Thank you all for coming. Our next speaker, Christoph Pasch, is a networking architect at Apple and first presented here at the Analog stage in 2016. He's been working on transport layer networking since 2010 and has recently shifted his focus to improving the network properties for end user experience by exposing measurement tools leading to today's presentation, Responsiveness under Working Conditions. We're happy to welcome Christoph back to the stage for his second Analog presentation. Here we go.
Okay, all right. Thank you. Hello, everyone. Thanks for coming. Thanks for coming back from the coffee break. I'm Christoph. I'm an engineer at Apple. I'm here with my two colleagues, Randall and Stuart, who are right here in the audience as well. We're here, so after the talk, you can come and discuss with us about what we presented. So about 2 years ago, we started this project working on what we call now responsiveness under working conditions. But before I get started, I want to kick off with a little survey here. So over the past 2 years, we have all been in this pandemic and we have been forced to work from home, spending our days on video conferencing, right? So please raise your hands if during this time you experienced problems with the video conferencing. Almost everyone, I guess the ones who don't lift their hands, keep their hands up, please, keep their hands up. So yes, so almost everyone, right? So who upgraded their internet service during this time? To a better or faster internet, right? Yeah, quite a few as well. So for whom did all the video conferencing issues go away? For you, they all went away? Okay, well, we'll have to talk to you later. How do you did that? But so here we are, right? We have serious problems with our internet. We pay more money to get better internet, and still we have problems with our internet. So something is wrong, right? And we should do better. And people here in the room, we are able to do better. So I will show you what we have been ignoring for the past decades when we are measuring performance on the internet. We call what we have been ignoring is responsiveness under working conditions. And I will show you what you can do to improve the responsiveness for your networks and your devices. But first, let me take a step back and let's think about what is actually good internet. Well, it's all about the throughput, right? After all, there are all these tools available to us to measure throughput. We have iPerf, right? That's basically our basic tool for measuring how good our network is. We use speed test tools to see the capacity of our network, right? Whenever we buy internet, we choose between a capacity plan. We choose either 100 megabits per second, 600 megabits per second, maybe a gig. When we buy a new phone that has 5G enabled, the first thing we do, we measure the capacity, how fast can the phone transmit data. And after all, at the beginning of the internet, 56 kilobits per second, that was really not enough. And so we upgraded to megabits per second with DSL. And today, everybody has gigabits per second with fiber to the home and 5G. So there's a lot of focus on throughput. But we believe it's actually not all about throughput. Sure, in the early days it was, when 56 kilobits were really not enough. But today, everybody has easy access to 100 megabits per second at least, and 100 megabits per second is hugely enough for any 4K video streaming, right? So we believe that there are other factors that are important for good internet quality, namely latency and jitter. And we are used to measuring latency and jitter. Other factors like protocol conformance. There are standardization bodies like the IETF. They are working hard to create new protocols that improve the performance, that are more reliable, that have better security and privacy properties. And we need the internet and the networks to support these protocols. And finally, yes, it also is about throughput, right? But so we have been measuring latency for a long time. We all know how to use ICMP ping. And we are very used to use this as a measurement tool to qualify our networks. But what is wrong with those kind of traditional latency measurements? Well, first point is that when I, as a user, I'm browsing the web, I'm not browsing the web using ICMP ping, right? I'm browsing the web using HTTP, TCP, QUIC, and so on. Nobody transmits any useful data over ICMP ping. Also, in the routers and the network equipment, usually ICMP ping gets a different treatment. It may use a different priority queue. It may use the control plane, not the data plane, right? But the traffic that the users are using, TCP, that uses the data plane, okay? So this use of an artificial protocol to measure latency is just wrong, right? And the second point is, very often when we measure latency, we do it when the network is idle, right? We do it at the beginning, before we measure capacity. But I don't want my network to have low latency when it's idle. I want my network to have low latency when I'm actually using it, right? So we believe that this use of those unreal conditions leads to a wrong impression of latency. And we believe that there's a need for a more realistic latency and responsiveness measurement. So back to my little graph that shows what means good internet. Well, we believe we need to add responsiveness under working conditions into this. And this talk is about what is responsiveness under working conditions and what you can do about it. So let me explain you. What is responsiveness under working conditions? And there are a few measurement principles we follow when measuring responsiveness under working conditions. First of all, I mentioned earlier this use of artificial protocols. So when we measure responsiveness, we use the most common protocols, which means HTTP. Almost all of the internet's traffic today is running on top of HTTP. It's not only used for web browsing, it is used inside applications when they are fetching any kind of content from the internet. Everything today uses HTTP. So it's important that we use these kind of protocols when measure it. Second, we create what we call working conditions. And this is the kind of conditions that you are experiencing when you're actively using the network. What is a working condition? Well, if you receive an email with a few attachments, if you're an engineer, you're downloading an SDK from the web. If you're a designer, downloading or uploading the images that you created, right? Even when your kids are watching a movie on Netflix, all of this puts the network into working conditions. And that's when you want low latency. Now, putting the network into working conditions, what effect does it have on the measurement? It means that you are measuring the network's ability to multitask. Is the network able to provide high throughput for the movie that your kids are watching, while at the same time providing low latency for the web browsing that you are doing, or the video conferencing that you are doing? So it's about multitasking in the network. But it's also about agility, right? If you are watching a movie, you want to be able to skip forward in the movie and the network to immediately give you the updated video frame, right? Is the network agile enough to react quickly to the user input? So those are the two measurement principles. It is using common protocols and working conditions, right? So let's dig a bit more into the working conditions. What is the goal behind the working conditions? First of all, we want to push the network to its capacity limit, right? So that it's fully being used. Any file transfer, any email, all of these kind of transactions are using the network at its full capacity. So we want to push the network. Now, how could we do this? Well, we could just flood the network with UDP traffic, right? But the problem with that is it's not very realistic. Nobody in real life is doing that. So the way to create those working conditions is by creating multiple bulk data transfers using HTTP, using standard congestion controls. And so they push the network to the capacity limit while remaining realistic. So it's a realistic use case, like, for example, transmitting some files, sending a message with a photo attachment, and so on. And again, we use the common protocols like HTTP for this kind of traffic generation. So you have to imagine in this measurement methodology that we are creating this working condition first, and then we measure the latency. Now, during this latency measurement, we measure it in two different user representative scenarios. We send HTTP GET requests for a small object. So again, we are using a very common protocol, HTTP. That's the same scenario that you would use when you are visiting a website. And we measure it first on separate connections, right? We have those load generating connections, and then we have the separate connections, and they are measuring the latency, sending those GET requests. Now that allows to measure the network's ability to multitask. But then we are also sending GET requests on those connections that are generating the load, making sure that the network is able to be agile and quickly react to user input. As we are measuring this, we collect the HTTP request response times, which then is the latency end-to-end. So we created this measurement methodology, and we started implementing a tool in macOS, available as a command line tool called Network Quality. For those of you who have a recent macOS build here, you can use it. But then we also standardized this methodology, and we reached out to the community. There's now, for those of you who are running Windows or Linux, there's an open source tool available based on the Golang environment. So you can run a responsiveness test on any kind of platform nowadays. Even IPERF 2 now created a responsiveness measurement with the bounce back option. So for those of you who are used to using the latest IPERF 2, you can use the bounce back option to measure responsiveness. And finally, the Ookla speed test app also adopted now the responsiveness measurement. So I invite everybody here in this room who has a smartphone with the Ookla speed test app installed, or whoever is on his laptop, go to speedtest.net and do a speed test right now and see how is the responsiveness here at Nanog. I tried it earlier this morning. I had more than 1 second of latency on the downlink. And so I invite you all to try it out right now. And you can experience it for yourself in the speed test app. So you see this little screenshot here, right, from the Ookla speed test app. And I want to zoom into this a little bit more. So on the left side, you see the responsiveness, the idle latency, 6 milliseconds, perfect. You can do a video call at 6 milliseconds 6 milliseconds latency. Then in the middle, you see the downlink latency. It is 3 seconds. I guess we all agree that 3 seconds of latency is not good, right? Imagine you're on a video call and suddenly your latency jumps to 3 seconds. This video call will no more work. If you're playing a game, it will just be a very bad experience. If you're playing an online shooter game, you will just die right away. So I guess we all agree that 3 seconds is not good enough, and we need to do something about that. But there's something more about this screenshot here. It is that Ookla speed test, we all use it. Everybody uses it. Our end users are using it. And they will start using speed tests and see those numbers and start comparing networks with each other, devices with each other, right? So they'll start complaining and ask questions. So we need to be ready to answer those questions and make sure that our networks will show good Ookla speed test numbers, right? So let me show you what we can do on the network side to improve the responsiveness. And before I get into this, we first need to understand a little bit more about what does responsiveness actually measure? What does it create, those working conditions? And imagine you have this data path from the phone on the left side and the server on the right side. Traffic will go through the internet to the ISP. At the last mile, there will be a CMTS or a DSLAM. If it's a cable access, there will be in the home, there will be a cable modem. After that, there will be a Wi-Fi access point. And along this data path, there will be a bottleneck. Some element is limiting the capacity. It could be the ISP if you have subscribed to a 100 megabit per second service, or it could be the Wi-Fi access point if you are far away from your Wi-Fi access point and the signal quality is bad. So you have this bottleneck in the middle. And now, in the traditional latency measurement way, what will happen is the server will send this latency probe through this bottleneck, and this probe will go very quickly through the network, through the bottleneck, over to the phone. So it's a very fast latency measurement. This explains the 6 milliseconds I showed you earlier on the slides, right? Now, what does working conditions do? If I am creating working conditions and I am generating traffic on the network, what happens is that this traffic starts piling up in the bottleneck. You see this standing queue building up, and then this latency measurement probe, right? This latency probe that at the end is sitting behind all of this other traffic. Now what happens is, because this bottleneck has a certain capacity, and let's say I measured this morning here at Nanog, I measured 10 megabits per second. It's kind of slow. So imagine how those 10 megabits per second are slowly draining out of this bottleneck. And this latency probe is queued behind all of the other traffic, waiting for the previous traffic to drain until finally it reached the phone. This explains the 3 seconds I talked about earlier, right? So let's recap. What causes low responsiveness? Well, first we have those data transfers, like an email attachment being downloaded, photos being sent or received, a movie being watched, right? Then we have those data transfers that are creating working conditions. These working conditions result in an increased buffer occupancy in the bottleneck router, right? And this buffer occupancy creates this high latency, low responsiveness that you are experiencing, which again will cause a bad video conferencing experience. So what can we do about this, about the network side responsiveness? Well, first of all, we need to understand why is this buffer building up in the bottleneck router. So in this example, right, where we have the server sending data to the phone, the transport layer doesn't know about the bottleneck's capacity, right? The only way for the transport layer to learn about the bottleneck capacity is by probe the network and by gradually increasing the transmission rate, right? The transport layer has no clue. So the way it's doing this, and it's increasing the transmission rate, probing for capacity. Eventually, the transport will be sending at the bottleneck's capacity, and it will even overshoot. Once it overshoots, then we have a queue building up at the bottleneck, and this is the queue that you see right there, right? Now the bottleneck is still draining at its regular capacity, slowly one packet at a time. So we have this standing queue sitting there, and the transport layer only learns about it once a packet gets dropped, and then the transport layer will start slowing down its transmission rate. But in the meantime, we have created this queue that is just waiting to be drained. So the problem really is here that the network buffers are just too big, right? And they need to become smarter at managing this queue and letting the transport know at what is the right transmission rate. So let me show you a little bit more in a graphic way of what is happening on the network. So if you have on the top, you have the good put at which the data is being transmitted, okay? Good put at the beginning, as the transport is ramping up, is gradually increasing. Because the transport layer is standing below the bottleneck's capacity, there's no queue up in the bottom, buffer occupancy is 0, no added delay. But as the transport is overshooting, what we see then is, well, good put is not increasing because the bottleneck's capacity is stable. It cannot create more capacity, right? So good put is stable. But now we have the bottleneck who is increasing the buffer occupancy, meaning there's more delay being added to the flow. Unfortunately, today, we are operating at this point. We have maximum good put, but also maximum buffer occupancy, which means maximum added delay, which means 3 seconds of latency. Where we want to be is there. We want maximum good put, but minimum buffer occupancy. So how can we get at this operating point, right? So as the transport is ramping up, at one point this queue is starting to build up, and we want the transport to oscillate around this optimal operating point, right? And the only way the transport can do this is if it gets a signal from the network that tells the transport, hey, please slow down. And if the network can provide this signal to the end users, to the end hosts, then the transport can oscillate around this point, and we stay very close to this optimal operating point. We have lowest delay while having maximum capacity. Luckily, there is a technology available that achieves exactly this, and it's called L4S. L4S is an industry standard developed by the IETF, and it stands for low latency, low loss, and scalable throughput. So it gives you the best of all the worlds, the lowest latency and the high throughput. There's a large community around it developing IETF, the L4S standard. And the way L4S behaves is that it notifies the end hosts early when the queue is building up. This notification uses the ECN mechanism, which is a very lightweight mechanism to allow to signal to end hosts when a queue is building up. The end hosts, when they receive this notification, they can react quickly and keep the queues low. So L4S is a significant improvement in responsiveness. It allows to bring the latency from several hundreds of milliseconds down to only several milliseconds. And it's not just an IETF standard. There's actually a large community around L4S. There has been an Interop event at the IETF, very successful in July of this year. There were 15 companies participating in L4S. Companies like Apple, Google, Comcast and Charter were there, content providers like Netflix, equipment vendors like Nokia, and so on. A total of 7 bottleneck implementations were tested, implementations on DOCSIS, cable modems, CMTS, as well as Wi-Fi access points and 5G emulators. So there's a large community around it, and there's a lot of movement behind L4S to improve the responsiveness. The good news also about L4S is it doesn't need to be deployed everywhere on the internet. Only the bottlenecks need it, meaning only the CMTS, the cable modems, and the Wi-Fi access points. You don't need to update the core routers, right? Finally, at the L4S Interop, at the IETF, there were a number of end-host implementations, and they did a very successful demo of the ultra-low latency, how they were able to keep the latency at several milliseconds while loading the network at its full capacity. So L4S is the future, and so what can you do, or what can we do about this? So if you are an operator or vendor, we encourage you to start measuring responsiveness with one of the tools I presented, right? If one of you here ran the speed test while I was talking earlier, I don't know what number you observed. I'm sure some of you saw more than 1 second. So that's the kind of scenario we need to improve, right? So start measuring for responsiveness in your networks, in your equipment, everywhere. Make sure that your networks are ECN friendly so that L4S can be deployed easily. Also, if you're an operator, go ahead and ask the vendors about L4S. And for the vendors, implement L4S in your network equipment and participate in the Interop events so that you can provide the high responsiveness to your customers. I have a few references here on the slide that will allow you to get some more information about the L4S effort across the industry. So I've shown you now this responsiveness measurement metric, given you some pointers to some tools, and we have talked about how we can fix responsiveness in the internet. So the talk was supposed to be done here, and we would all be able to go get a coffee. Now, unfortunately, on this journey, we discovered something that we actually did not expect. And this is the story about server-side responsiveness. Let me tell you what this is about. So as Randall, Stewart, and I, we were working on this, and our goal was to improve random access in the movie streaming. So what does this mean? This means I'm streaming a movie and I'm skipping ahead. I want to skip ahead. I don't want to watch a trailer, or I want to skip ahead 10 seconds because I've already seen it. And we are all used to this experience because when we skip ahead, we get this little spinny wheel, we wait a few seconds, and then the movie starts again, right? And Randall, Stewart, and I, we were like, okay, this is a responsiveness issue. We'll have to work on our bottleneck, and we fixed our bottleneck. We made sure that our bottleneck had a high responsiveness, was properly configured, everything was perfect. And when we tried it again, the movie streaming, and we skipped ahead, it was better, yes, but it wasn't perfect. It wasn't instant, right? It wasn't right on the spot. And as we started digging into this, we realized that we forgot something. We only fixed half of the problem, because the servers are actually having a big impact on responsiveness as well. So let me explain you what happens on the server side. So a typical server-side stack has an IP layer, transport layer, a security layer, and an HTTP layer. Now, what is happening there is that inside the transport layer, you have the congestion control, right? That is measuring the capacity and the speed of the TCP connection, of the bottleneck link inside the network. Now, this congestion control is actually limiting the speed at which data is draining out of the server. And so what happens is there's a queue building up in the transport layer, in the TLS layer, and in the HTTP layer. And if you start digging in some server implementations, you have several megabytes of data queuing up for every single TCP connection. And if you have even a staggered server deployment in your CDN environment, where you have, for example, one server terminating TLS and HTTP, and another server hosting the content, you have this kind of chain of buffers queuing up one after each other, creating latency up to tens of seconds of latency. And this was the reason why, when we were skipping ahead in our movie, we were not seeing the instant response, why we were still waiting for the spinning wheel. It was because data was queuing up on the server side. So servers have a significant contribution to responsiveness issues. There are many opportunities on the server side for overbuffering. It's in the transport layer, the TLS layer, HTTP layer. Any layer you can imagine on the server side has the potential for adding additional buffers and causing additional problems in terms of latency. And the impact on the user experience is huge. Skipping forward in movie streams, once you fix the server-side latency, it is instant, right on the time. So you skip ahead and immediately the movie continues. It was mind-blowing, this experience. Another aspect is adaptive bitrate algorithms, like HLS, that are trying to download or stream a video at the speed of the bottleneck. If you have a lot of data queued up and the adaptive bitrate algorithm wants to adjust the bitrate, the bitrate algorithm needs to wait for all of this data to drain before this new bitrate can be sent, right? We have seen, when we are trying this out in our new server environment, we have seen a reduction of 20% in the stall rate for video streaming. Any use case that uses HTTP2 has huge benefits with a better responsiveness. Whenever you are sending a large HTTP stream multiplexed on a single H2 connection with another smaller latency-sensitive stream, high responsiveness will be a big benefit for those use cases. Anything you do on the internet, web browsing, and if you have a stock application, weather forecasts, if you're getting driving directions in a maps or driving navigation app, all of these use cases benefit from a higher responsiveness. So what you can do here is that you can reduce buffering in the server side by working on the transport layer. There are options available in Linux, for example. It's called TCP not send low watermark, that allow you to limit the size of the buffers. Across the networking stack, in the TLS layer, the HTTP2 layer, everywhere, you can work on reducing those buffers. Buffers can be everywhere, so be mindful. When we worked on improving ours, we were digging through all of those buffers to figure out where this was happening, and we found many places where we had to do small adjustments. So here's what you can do, right? With the tools that are available, like the network quality measurement tool on macOS or the Go responsiveness measurement tool, you can simply start hosting some files on your servers that allow you to point those tools at your server, and then you can start measuring the responsiveness of your own server. So if you do this, you will be able to see how does your servers behave in your environment. And then you can start tuning those buffers that you know about and start playing around, and you can see whether or not it helps for your responsiveness. And try again and see if it improves your customer's user experience. Believe me, it will have a big impact for many of your users. I have some resources available to you about the tools and L4S that you can look up on the slides that are online right now. But I want to conclude my talk with some closing remarks before we go into questions. First of all, better responsiveness gives a better user experience. We have shown that responsiveness under working conditions is an important metric today that can help improve the user experience. Video streaming will be just so much better with a good responsiveness. Those tools that are available to you, we really encourage you to start using them. The Ookla speed test that you ran here, it shows you that there's a lot of work to be done, right? And the work to be done, I've given you some pointers about L4S that will allow to fix the network side responsiveness. And if you are a CDN, content provider, or streaming provider like Netflix, go work on the server's buffer management to make the streaming and all of the other HTTP use cases better for your clients. And so with that, I would like to thank you for your attention. I'm ready to take questions, and I would also invite you or anyone who is interested to come talk to us later after this talk. We would be happy to discuss with you and help you on improving your responsiveness. Thank you.
Hi, Vinod from Keysight. Great presentation.
Thank you.
3 questions. One is the problem on the server side mitigated to some extent by load balancing? And second is, how much of this can make it into the ASIC into the ASIC on the first mile from the client, right? How much of the L4S can be implemented in the ASIC?
Yeah.
And does the problem become worse or has to be managed out of band for admission control? While the data throughput is happening, does connection admission control is a separate problem, needs to be managed separately outside of data latency, or it can be managed in band, as just like TCP sends, it's another stream of data, while the admission control falls into the same category of problems, or not?
Okay. Thanks for those questions. You can stay there because I might ask some clarifying questions. So your first question was if load balancers on the server side will help on the server side responsiveness, right? So on that question, the thing is no, load balancers don't help because it's not a question about server scaling or capacity. It's a question about, so every single TCP connection that is created to the server is running at a certain speed. And that speed is driven by the bottleneck capacity in the client's network usually, let's say, right? And so that's not a question of server-side scalability. It's a question of the bottleneck. And so this limitation of the capacity of this single TCP connection is piggybacked all the way to the server inside the TCP congestion control that is running on the server side. And what happens then is that because this TCP congestion control on the server side is like yet another bottleneck, right? And this yet another bottleneck means that data will be queued on top of it, right? And so it's not a question about server-side scalability or fanning out and load balancing. It's just about buffer management for a single TCP connection because a TCP connection is this additional bottleneck that is causing more buffering. I hope that answers your first question. On the second question was whether L4S can be implemented in the ASIC. So L4S is a very simple mechanism. It only requires to have the bottleneck provide frequent marking on those packets that are being transmitted, right? And sorry?
Anything on smart NICs?
Smart NICs?
Yeah, anything smart NICs should be aware.
Yeah, it should not be a problem of implementing L4S in a smart NIC. Because, I mean, smart queuing has been implemented in the ASIC for a long time, and it's very common. So L4S is just another mechanism for smart queue management to provide this additional information from the network to the end hosts. I'm sure Stuart wants to provide another comment on that.
Yeah, I'm Stuart Cheshire from Apple. I just wanted to clarify, because when you asked the question, there might actually be 2 different things that you're talking about. Because L4S has 2 components. There's the end systems, because the internet we run today is based on the end-to-end principle of put as much of the brains as possible in the end systems. And those end systems are responsible for sending the right amount of data into the network. Not too little, so you leave capacity idle, and not too much, so you overflow queues. So part of the L4S algorithm exists in the end systems. But those end systems can only adjust their rate if they get the right signals back from the network to tell them when they're going too fast. So like many of these things, it's a partnership. There's brains in the end systems and there's brains in the hops through the network. So when you were asking about ASICs, I wasn't sure whether you were talking about routers forwarding packets or end systems. I mean, I guess the answer is yes in both cases, because anything you can do in software, you can probably do in gates if you try hard enough.
Talking about the smart NIC on the end system, say, if there's anything that the smart NIC can piggyback back to the application on the local system.
That depends how smart the smart NIC is. If it's doing simple TCP segmentation offload, where the host stack ships a 64K segment that gets sliced up, that is relatively easy to do. Packet pacing is really important because a 10 gig line rate burst of a 64K thing is a big burst of packets, and that burst has to be smoothed out somewhere. So pacing is really important. If you're talking about offloading the entire TCP or quick state machine onto a smart NIC, then the responsibilities go with that. We have Reno congestion control, we have Cubic, we have Compound, and now we have L4S. So if you wanted to do L4S entirely in hardware offload, you would have to implement that. But I don't see that as being a major impediment, no more really than Reno, Tahoe, Cubic.
Hey, David Tuber from Cloudflare. Great talk. Really enjoyed it. Question about the server-side responsiveness. You mentioned that. So you mentioned about congestion control. Have you done, or is there a plan for any analysis on what is the optimal congestion control mechanisms for server-side implementations? And if not, like, what is your gut feeling, or like, what do you think is probably going to be the best congestion control algorithm? Because there's BBR, Cubic, Reno, all those.
So in terms of congestion control, one problem today is with Cubic, right? It is congestion control that is looking for a packet loss and tries to fill the pipe as much as possible. So it's kind of a congestion control that has a tendency to create this kind of network side responsiveness issues, because it always tries to put as much data as possible into the network. Congestion controls like BBR are smarter about it and are definitely better in terms of buffer bloat, but it is a very delicate balance because BBR has its own problems and its own instabilities, right? So we believe that the right way forward is to have this cooperation between the network and the end host with L4S, where the network is providing just a tiny little bit of information back to the end hosts so that the end hosts can easily find the best operating point at which they can use the full capacity of the link without creating a queue. That is, in our opinion, the long-term solution for the internet. Thanks. So unless there are any other questions, I guess we can go for a break. Thank you very much.